And we are back once more. And we're doing some more air friction. This is an example, a slightly more complicated example of air friction when you have multiple forces involved. And the classic one that you see is a skydiver, anything that falls through the air. It's still, a calculus problem. It's another reason air friction is complicated, and a lot of students tend to cringe when they see air friction actually in a problem, simply because it's a velocity-dependent force. And in case of a skydiver, this is what Newton's second law gives us. We have gravity pulling you down in the direction of motion. Air friction is resisting the motion. That's why we have that minus sign there, negative kV. And that's the equation that we get. We can solve this for acceleration if we wanted to. If we divide through by the mass, then we'd have the acceleration of gravity minus the second term, k over n. These are constants times the velocity. So it's a non-constant acceleration. We have no choice but to do calculus if we want to figure out what happens to this person as a function of time, as your clock is ticking. So what we do, in order to get time in the mix, is we use our definition of acceleration. We know acceleration is the derivative of velocity with respect to time, and that's really the key. So we write down a first-order differential equation. We have acceleration on one side, on the left, and then we've got the forces from our force diagram over here on the right-hand side. Okay, and what we always try to do is we try to separate the variables. So if, in this case, if we bring that dt up on the right-hand side, it looks something like that. Now the only way we can get all the velocities together on the left-hand side is if we divide through by that total, everything in the parentheses there. So rewriting things, our equation looks something like this. And we've successfully separated the variables. Once you do that, you can integrate. This is the calculus step right here. And typically, what we generally do is, when the skydiver jumps out of the plane, vertically the velocity is 0. And that's when your clock starts. So time-wise, we start at time equals 0, and we let the person fall. We let this object move for however long we want. I'll just generically call it t. Now, corresponding to this, over on the velocity side, your initial vertical velocity is 0. Okay, you're just stepping out of the plane or whatever it is. Okay, and what we're after is, after so much time clicks away, what's your final velocity? That's really what we're trying to solve for. Okay. Well, on the right-hand side, all of us should be able to do this. That's just whatever your time interval is, however long your clock is running. The left-hand side is trickier. Fortunately, we have a bunch of constants. Gravity's constant, k and m are constants. That's not going to screw up the math on us, and effectively we've got dv over v. So we've got a natural log on the left-hand side. We've got a natural log of that entire denominator. Okay. We're going to have to evaluate this still from when your velocity is 0 to the final speed. Okay, and what's more is because that constant is in front of our variable, we have to do chain rule. Okay, we have to do 1 over that constant out front, so negative m over k pops out. Okay, it's a little bit trickier. If you're new to calculus, if you haven't really done this much in your calculus class, we will do many examples in physics and get you used to this. But that's really the trick. That's that so-called chain rule. To evaluate things, we have to plug in our top limit, which is the final speed, and then subtract what we get for the bottom limit, which is 0. Before doing that, I'm just going to go ahead and I'm going to divide through by those constants and put them on the other side. So negative k over m with time over on the right. Now we can solve this. Okay, so we can plug in v final and subtract what we get when we plug in 0 for the speed. That's just natural log of gravity, 9.8. We've got those constants, and then our time interval on the right-hand side. Now this is all the same as natural log of that divided by gravity. Okay, just doing algebra now. There's no more calculus left. This is just algebra. Let's see. Get rid of natural log. We have to e both sides. And I'll also simplify what's inside the natural log. So g over g is just 1. Then our second term is going to be minus this k constant over mg, which is the weight, times the final speed. And then we have an exponential function on the right-hand side. Okay. And if we go ahead and solve for v final, I'm just going to go ahead and write down the final answer. Our final speed really is our velocity as a function of time. We're going to have these constants out front. And then in parentheses, 1 minus the exponential. That's our final solution by applying Newton's second law, F equals ma, to a skydiver, or pretty much anything that's falling, if these are the only two forces that are affecting the object. Okay. What does it all mean? What does this look like? Well, what this is telling us, if we were to make a graph of this function, or velocity on the y-axis, time over here on the x-axis, if you plug in 0 for time, e to the 0th power is 1, so we have 1 minus 1, it starts at 0. That's cool because that's what our initial condition was, way back up here. Our initial condition, we said that it started at 0 speed when you jump out of the plane. Now as time gets big, okay, if you plug in a big number for time in this expression, this exponential function goes away, it approaches 0. But we have the second term left, and it's a constant term. There's an asymptote in this graph. The velocity increases exponentially and then tails off to a constant speed. That's what we call our terminal velocity. And it's the weight divided by this constant k that we have with the air friction. Okay, that's the big deal. Okay, for people it's something like 120 miles an hour on average for human skydivers. That's pretty fast. That's without a parachute. Now, the only other thing I wanted to mention here, we can find the terminal velocity at least straight from F equals ma. At terminal speed, the acceleration is 0. Because by definition, you're going so fast that your friction force upwards is matching and balancing the gravity going downwards. And so this has to be true. Okay? So when you solve for speed, you get the same thing. Weight divided by that k constant. That's our so-called terminal speed. Okay? So we can get it right from F equals ma if we just know the definition of terminal speed. We can get it by doing the fancy math and getting this weird function down here, which allows us to find instantaneous values, and that can be useful. We can find position as a function of time and acceleration as functions of time, the usual ways, but I just wanted to go through these steps of how to do the calculus originally. Okay, separate variables, take the integral, and then do some algebra to get that final expression down here. Okay, so until next time, we will see you later.